thank the organizer of the workshop for organizing the workshop. And I have first to, so preparing my talk and all the talking yesterday with Eamon, this is supposed to be a workshop also for PhD students and people not very familiar with representation theory of finite groups. So I was thinking that if you really want to get a bit, understand a bit what's going on at the reduction theorems, I will speak just about one reduction theorem and just one counting conjecture. For more, you can also come to the May workshop on counting conjectures and beyond. So the conjecture I will talk about is the Mackay conjecture. Stated by Mackay, and the idea is that G be a finite group P a prime, and capital P should be the P subgroup of G. And then he was trying to find representation theoretic analogs, what was going on during the classification. So he was wondering how these global local principles in the proof of the classification can be seen from the representation. And he observed that the number of ordinary P prime characters of G equals the number of irreducible P prime characters of the normalizer in G of the pseudo P subgroup. So we're here in a situation where we really just work with the ordinary characters, so characters over capital G, and with a nice and easy to state condition that the dimension of the corresponding module should be P prime. And that's something you can read off from the value of the character just by looking at the value at 1, and it's P prime. So, and since it was during the classification, Mackay looked for, of course, first at the prime 2. And for this prime 2, this conjecture is true, just that proving that took a while. So it was announced 2015, appeared 16 in print, and I would like to tell you how this was proven. So not only people doing group theory can use a classification, so the idea was let's use for proving conjectures like that the classification and our knowledge about simple groups and simple groups of Lie type in particular. So David Craven was telling me that this should be a circus and we should all combine each other's talk. So the idea is, Alan Henke was nicely saying, almost all simple groups are groups of Lie type. So how can we use things, the theory that Olivier and Shay explained to us about the finite reductive groups in order to prove conjectures like Marcus has stated. And there were several attempts to do that, but I think one of the first nice reduction theorems that came up by Isaacs, Mahler, and Navarro, and that was 2007, and they were saying, okay, what we want is that the Mackay conjecture is true. If every simple group satisfies a set of conditions, the so-called inductive Mackay conditions for P. And I will speak a bit on that later. So let me shorten that. So you might have now a couple of questions, I hope at least, because I'm trying to answer those in the next 45 minutes, 50. Namely, you might ask, what are these conditions? And I can tell you, they involve, don't be a bit patient with me, I will give you that later, but then the second question is, how can you prove that? And that will be the next thing that I will tell you about. And the third thing that you might also ask is, for which simple groups can you prove those inductive conditions? The idea is you have to somehow make visible the representation or relate the representation theory of a simple group with the representation theory of a general group. And how do you do that? You probably try to say, okay, let's assume that G has a normal subgroup N, and then you try to understand the representations of G in terms of the representations of N and subquotients. But that's a very well-known subject that goes back to Clifford, and that was already stated in Culver's talk. So let me be here a bit modest and let us just review a bit of Clifford's theory, as you might have seen in your early years of study. So assume that you have a normal subgroup N of G, and we try to understand characters of G and characters of N. And what you see is G acts on N, and hence on all the irreducible characters. And on the other hand, there are subsets in the characters of G that are indexed by characters of N, namely these are just the irreducible constituents of the induced. And the version of Clifford's theorem is a bit different than what Culver stated yesterday. But one should remark this is the statement even is true from many characteristics. So the first statement is the constituents of the restriction of chi 2n form a G orbit and this action also has another consequence, namely normally I told you if you induce your character you can get plenty of constituents. So induction is normally not a very good way if you really want to study simples. But in the context of Clifford theory, there's a nice situation. Namely, if you look at those characters, these are characters that are living above theta, but are living on the stabilizer of theta in G. So this is G index theta is described sometimes as inertia group, is sometimes denoted by a capital I, index G of theta. And the point is there's a one-to-one correspondence between all the characters lying above theta of G and those that are lying on the stabilizer. And this is really just a one-to-one correspondence. Why is this interesting? We are interested later in p prime characters. You know what happens while, with a degree when you induce a character. It multiplies with the index of your stabilizer in G. On the other hand, you also know so if you want to have here a p prime character, G theta has to have p prime index, and this phi has to have been p prime. So many questions that you have on characters here can be answered by looking at the characters here. So it makes sense to have a special look to the situation where your theta is invariant in G. But having only that, let's dream a bit more. Let's dream that, in fact, chi is an extension of theta. Then we can very nicely describe this set. Namely, all these characters of G lying above theta can be written as products of with a character eta of G over n. So this is coming from the tensor product of the corresponding matrices. It's called lemma of Gallagher, and so it tells you if your character extends, all your characters can be just in one-to-one correspondence with the characters of the quotient group. But whenever you have really actually once worked with characters, you know not all characters extend, by far not. So how do you use then? If you have that your theta is invariant but does not extend, what you can still do is you place your character, your extension came from a extension of a representation. So, okay, the only way to now deal with the situation is to instead look at what's so-called projective representation. So, I will tell you a bit more on that. These projective representations are really just maps going from G into the matrices and are combined with a map going from G cross G with the property that if you multiply two elements, two of those matrices, it looks like a homomorphism, just not right. So you have to multiply with a scalar. One could also rephrase that as saying this map is not actually a morphism, but it induces one if you would see the corresponding map that goes instead to GL to PGL. Okay, but it should do something with theta. So the idea is if you restrict it to n, you get actual representations, a representation affording theta. And if you are in the situation that your x or your y are in n, this factor vanishes. So this tells you that on certain cosets, on certain values, your alpha is actually 1. So this alpha is called sometimes, I should say, factor set, and other people doing cohomology graph group might say this is just a 2-co cycle. Yeah, the point is that P and alpha are by far not unique. not even up to similarity. There's a bit of ambiguity here, but it, you know always that there exists something like that, and it has the same role as before your extension, namely if your character chi was lying above theta, then chi is a character of Q tensor P, where Q is a projective representation of G over N with inverse vector set. So normally, if you multiply elements in P, you make a mistake. And the idea is that you multiply with matrices Q that make just the inverse mistake, and then it gets really multiplicative. So seeing all that, you might end up to understand that if you're just looking at characters, the really interesting idea is to look at triples G and theta, and they are called character triples. Where N is normal in G and theta is a character of N, but that is normal in G. This is called character triples, and quite a lot of ideas working with solvable groups is looking at character triples of these groups and then manipulating them. And if you apply only that, then the first idea is, if you try to apply it to Mackay, is that you want to make the normal subgroup visible, and therefore one uses the relative Mackay conjecture. And it's just saying that you compare these sets in the presence of a normal subgroup. So it's saying take a character of the center of G, and then the number of P prime characters of G lying above nu should coincide with the number of P prime characters of the normalizer of nu. So I'm sorry so I have explained here what is a P prime, what is the set of P prime characters. I have introduced there the characters of a group lying above a given character, and this is the intersection of both sets. And the relative Mackay conjecture says, okay, this equality even holds true if you partition those sets according to the characters that they are lying above. And just looking at this relative Mackay conjecture and quite old ideas from Clifford, you can get a first reduction. So you make an inductive proof, and where you end up, I think this must be on page 4, using just that for P-solvable groups, this relative Mackay conjecture is true, and then you say, a minimal counterexample has to look the following way. So the minimal counterexample for the relative Mackay conjecture has to have, must be a group and it has a normal subgroup, is normal in G, such that N is isomorphic to something like that over something central, for S being being simple. So what you would be first looking for is normally where is my simple group sitting, and it's sitting quite low, but there could be something central underneath. So S hat is what's called a universal covering group of S. That is something central in all that. And furthermore, you see G is generated by N and the normalizer in G of a group Q, for Q being a pseudo P subgroup of N. So voila, here's your simple group in your minimal counterexample. Okay, it's not a simple group, it's a universal covering group, and it's a R direct product. So what you have a situation is that you have a normal subgroup, you have big group G, and you want now to say, so these are groups that you should know somehow from knowing the representation of simples. Then you want that they are relating to the normalizer in N of Q. That would be the normal Mackay conjecture. These would normally relate P prime characters of N with P prime characters above here. And you would, and what you now want to study is to say, I want to count the P prime characters of G in terms of G P prime characters coming from here. So basically, I want to say that the P prime characters of N have the same Clifford theory as the P prime characters above those characters in here. So in order to do that, what one was introducing, or is nowadays introducing, is one is saying, both characters here give character triples, and we want to tell when we say that one is smaller than the other if they corresponding characters have the same Clifford theory. So this is the order on character triples. So this was not in the Isaac Muller-Navarro paper, but after rewriting and reworking on reduction theorem, we figured out that in fact what we are doing, we're using that. So let me first say something. So if you are not really with coming from this from a Sylo 2 subgroup, the idea is that H is a subgroup of G and is a normal subgroup of G. G is NH, and the centralizer of N is inside H. Then we write G and theta bigger or equal than H and pi for two character triples. So how do you now pin down that two characters have the same Clifford theory? So probably you look at the projective representations, that's the only thing that you can really investigate, and say, the cocycle should be equal. So if there exist two projective representations P and P prime with vector sets alpha prime associated to beta and phi, such that alpha on HH is the same as alpha prime. So now everyone is saying, so look at the second cohomology group, the element, it's the same, fine. And then the problem is if you really actually work with that in the reduction, you somehow, it's like you can now compute and count characters of G lying above theta, but it's really just that G that you can say something. So what is added is for every element X in the centralizer of N, you know that those projective representation give you on this element just scalar matrices. That's an easy consequence of the lemma Juve, that there are scalar matrices but you now say the scalar must be the same. So if one is an identity matrix, the other has to be the identity matrix. If the one was, you can also reformulate all that and say, okay, what's happening if my theta extends? So first of all, the phi has to extend, but on the centralizer of N in G, you will cover a linear character, and these linear characters have to be the same for the extension of theta and for phi. That makes, for example, the idea is if in the centralizer of G of N there was a normal subgroup in there that you could quotient out for theta, so that the extension of theta was a lift, then it's also an extension for phi. So the
N is H intersect N?
Yeah. So, yeah. Thanks a lot. Yeah. So, let me make a couple of remarks here. So, if my two characters were P prime, then it's very obvious that the number of P prime characters above theta coincides with the number of P prime characters of H lying above phi. Second, but we didn't have, so what we want is that we will take N as somehow like an S hat. So somehow we have to go from the S hat to the R's product of S hat. And what you see is that this order relation that we have put on the character tuples is compatible with constructing direct products and Wies products. So if people like Gunther or Olivier or Jay study is a situation where they look at S hat. S hat is a universal covering group of a simple group, so basically it's a group of Lie type, and then they embed it into a bigger group that acts by automorphism. Then if they have studied that and have found characters that are in an order relation, you can somehow say something about characters that live on the R-steric product, and the overgroup is then a Wies product. The Wies product is that you make the semi-direct product with a symmetric group when these factors are permuted. And why is this that cool? The point is, if you have chosen this gamma to be all the automorphisms that are acting on your simple group or in your universal covering, on this group, there won't be any more automorphisms than those. So, but we have said in our minimal counterexample, our n is not too far from there. So there exists an epimorphism going from this R-steric product of universal covering groups to n. Just what we see is that G is normal, has as a normal subgroup our n, but G might be any group. But what we know is that the automorphisms that G induces on n are not that different than those. So the cool thing about this reduction theorem is that they are now saying, if you have two characters that had the same Clifford theory in here, it will have the same Clifford theory in any overgroup. That was somehow, I don't know, I have written, I think, 3 reduction theorem down with 40 pages until I realized that's the key, really cool thing about this relation. So let me give you this theorem, which I nowadays call butterfly theorem. So the idea is that n be the normal subgroup of two groups, of G2 and G1. Then you can study the map that goes from GEI into the automorphisms of n. So GI acts on n, so there's a map going to the automorphisms. Assume that H2 is so what you want is I have studied my situation, my characters in my character theta and my character phi in an overgroup G1. And now I say, I'm not sure if G1 really looks like that. There exists a second group G2 and also second group H1. They all induce the same automorphisms. And the statement says, if we know that phi and theta have the same Clifford theory in G1, then they will have the same Clifford theory on the G2 side. So if G and theta is bigger than H and phi, then with ones, then it will have the same property with twos. So having the same Clifford theory should be just a property of your character. It shouldn't depend how n is embedded into G1 or G2. And this is really, that works. If you would have forgotten the second part about the central thing, this wouldn't work. So this is somehow really the specialty of this equivalence of this ordered character tuples. And that's somehow why this all works, because now you can say, oh, in my minimal counter example, I had the G was just inducing the same automorphism as I had studied there. So somehow, if you understand here the Mackay conjecture, and here have bijection of P prime characters where the characters have the same, you can conclude something for your general minimal counterexample. So what you get is now for inductive condition with this, those character tuples show up. And that's why the work on these conjectures on those conditions is so hard, because you have to have that. And it's basically you have to control Clifford theory via projective representation that haven't been studied that much. So let me write down the inductive Mackay condition. So I might, since I'm here anyway, just cleaning the board, I might like to add that in December a preprint appeared on the archive by Andre Marcus and his student Minuta, seeing that what we have here, and is here completely described in terms of characters, can happen to be a consequence of very special Ricard equivalences. And so this way to think about characters could get one day an interpretation, more module theoretic interpretation. And so the inductive Mackay conditions for S is something that's concerned the universal covering group S. S hat is the universal covering group of S. Then you take the pseudo P subgroup of S hat, and we denote by gamma so automorphisms of S hat stabilizing the pseudo P subgroup, and the condition holds for S if there exists a gamma equivalent bijection, call that omega, between the P prime characters of S hat and the P prime characters of the normalizer of Q in S hat, and the characters that are corresponding to each other via this bijection should satisfy now this property on character tuples. So, and whenever you have that, you can build these character tuples, both locally and globally and locally. And they should have, these characters have the same Clifford theory in the sense that they give ordered character tuples. And one might say, oh, I have never worked with such a thing. So your S hat might be an SLN, and this group is not so nice. But the point is, you can apply butterfly theorem, and whenever you take just your favorite group that induces enough automorphism, and you can plug it in, prove this property, and get proofs thereby its inductive Mackay condition. So there are, I should make advertisement, but I won't write it, so sorry for that. There are reduction theorems afterwards. So inspired by this nice result, they came far more, because there are far more counting conjectures. So we have seen the Alpern-Wade conjecture in Marcus' talk. There are also the Alpern-Mackay conjecture, there's the date conjecture, and all of them have been proven using a different adapted concept of the thing. The recent result is that you can also incorporate Galois actions, so actions of Galois automorphisms on that. I should name that this was done by Gabriel Navarro, by Tiep, by Carolina Valesio, and myself. Similar, one could also relate it to Fahrenheit zero conjecture, and luckily, once we didn't get a new inductive condition to prove. So it leaves us with the question, for which simple groups have you proven the inductive Mackay condition? So and well, the first groups that you normally start with are alternating groups and sporadic. So that's what Gunther looked at, Gunther Mahler, and the observation there is that the outer automorphism group of S hat is cyclic. And the nice thing is then that basically this equation on the lower equal can be replaced by just looking at the relative Mackay conjecture in enough cases. So there are a couple of groups that you have to check, and while it was also quite a long time after Mackay had stated this conjecture, so other people had looked into that. So there's a paper by Wilson that making sure that the Mackay conjecture holds for sporadic groups. There's papers by Micha and Olsen proving that for certain alternating groups, symmetric groups. So this leads to that the inductive Mackay condition holds for alternating and sporadic groups. So what else about groups of Lie type? And for groups of Lie type, I would like to focus on one case, namely for the prime 2. So now assume that our prime is 2 and that our S hat is just a finite reductive group defined over FQ. And I assume furthermore that 4 is dividing Q minus 1. if you are not so familiar with all that FQ thing, just think of the case where S hat is an SLNQ. So, what was seen in other talks in these groups is a so-called maximal split torus. So I'm looking here. T is my finite group. It comes from a F-stable maximal torus T that is embedded in a F-stable Borel. So I should also mention that. So B underline is an F-stable Borel. And together with the torus, you can also look at the normalizer in S hat of your torus, and so it's for that. And in our example, these are just the diagonal matrices. And S hat, then these are the upper triangular matrices. And the normalizers are the monomial matrices. So for the inductive condition, we have to look what's the normalizer of a pseudo 2 subgroup. And if you compute that, well, we want afterwards to make a character bijection, so we have because we want a bijection between the P2 prime characters on both sides. And what's happening, or what one is seeing, is that these groups that you get as normalizer of pseudo 2 subgroups or pseudo P subgroups are very far away from the world of finite reductive groups. So they are not reductive, basically. And that causes a bit of a headache, because somehow all your parameters for the 2 prime characters of your S hat are with lusty labels, dual elements, combinatorics, whatever we've seen, and then you want to relate that to something that's not in that world. So what was the observation that Günther made is, and also other people before in similar situations, is that this group of these monomial matrices has similar properties. So this N contains the normalizer of a pseudo 2 subgroup for 2 subgroup of S hat, and is stable under all automorphism of hat, stabilizing this Q. And so somehow Günther was also already in the reduction process telling him, that won't work if we are really in the inductive conditions, having here the normalizer of S hat of Q standing. So what happened then is that one was saying, we are in an inductive process, so we just have to go down. So what is possible is that you can place in the inductive conditions and this normalizer of S hat of Q by a suitable group that has similar properties, namely that is sitting between S hat and the normalizer of Q and is stable enough. This is enough. This is okay. So, so N can be used for verifying by inductive mechanics. So it's another technicality that comes up because we want to really work with the in the world. But this n now has a nice property, namely that if you look at the exact sequence, here you get a symmetric group, or here you get a Y group. So somehow, and the irreducible characters of the n can be described, in fact, with the theorem of Gallacher that is over there, this part C, namely all the characters that you get of the form of this form, where lambda is a character of T, eta is a character of quotient, and lambda tilde is an extension of lambda to n lambda. And I'm writing here that, yeah, you have the extension. But so this goes back in one way or another to far older results. The problem is if you would have here the situation of GL, your n would be a semi-direct product, you would know that all your characters extend. Just that here you don't have, for SF already, you don't have here a splitting of this group, so this n is not a semi-direct product, and then you have actually to work to see that your lambda extends. And the point is this is just here maximal split torus and so on, but it's reflecting more difficulties that you will get for other primes in other situations. But we have assumed this very nice situation for the prime 2 and 4 is dividing Q minus 1, and that allows us now that our 2 prime characters are coming from actually Hauss-Chandra induction. So let me recall a bit parts of Hauss-Chandra inductions that came up in talks by Olivier and Jay, but I'm afraid that I'm using a version that is similar. But so the idea is when one is starting trying to understand the characters of the finite reductive group, one was looking at characters that were denoted like that, but they came up as one was inflating lambda to a character of B. Well, you know that this T is a quotient of B, so you can blow up lambda to be a character of B, and then you induce from B to G. And if you now want to know what are the irreducible constituents, the nice thing about it, it's you can look at the endomorphism algebra, and this endomorphism algebra is a Hecke algebra, and you can explicitly describe the a basis of that. And it turns out that these irreducible, this endomorphism algebra is related strongly with the group algebra of a Weil group. So these irreducible constituents are labeled by the irreducible characters of the quotient of n lambda over T. So that makes that I can call the specific character by putting here an eta underneath. But be careful, this is not unique. In all that, I don't tell you that all this parametrization depends highly on the choice of lambda tilde. But it's a very algebraic thing, so what you now can ask is what's happening if I act with an automorphism of G on that, then you can say, oh, yeah, well, my T gets permuted, it gets not permuted, my T lambda. So You can control High-Chandra induction with respect to automorphism. So that's why one can, what we did, we looked at this parameterization and applied automorphism on it and looked how these different labels change. And we obtain that there exists a bijection between the 2' characters of G to the 2' characters of N that is given by the following. So it also involves that one has to go through all the characters of G, and in this case, in this specific case, it turns out that the only characters of odd degree are those that come from the principal series. A part of 1-2 exceptions for type C, but this is an introductory workshop. I want to tell you the main idea. And the main idea is it's all High-Chandra, and we can control High-Chandra because it's algebraic. The headache is, it's not always dividing Q-1, and there are more primes than just the 2. So what can I tell you about that? So in general, the inductive, the chi condition holds for S hat if P is 2 or S hat is not of type D or twisted D. So we all know that groups of Lie type have types indexed by these Dinkin diagrams, and well, for S this in work with. So this was done in many, although I should start with Olivier Brunat, then Marc Caban, then Günter Mahler, and myself. We have written in various combinations, papers, looking at specific simple groups at specific primes. And the problem is that we, at the moment, not always know how to ensure the equivalence of the bijection and the second property of that the Clifford theory of these characters is coincides. The main problem is we can't use High-Chandra induction basically, and in the moment you don't have High-Chandra induction, you have Jordan decomposition, and despite that Lustig has done a tremendous work, he's not answering if certain characters are permuted or not. So these questions, one has to think a bit that these Clifford theoretic questions, if these characters extend, haven't been there so long. So no one has answered that, and we have, and that was, I think, the main work the last 10 years, that we had to find ways to control those and to answer these questions anyway. And that's where I would like to stop.
What's the status on the local side? Do you have a view? Is it, have you worked out all the characters, parameterizing the characters in the local side? Or is that still
The parameters of the local side exist, but you can't, at the moment, it's not super clear why they have the stabilizers they should have. So that's also just in type D missing. And all the other types, that's been done, and I know, so you have a similar situation like here, where T is just the centralizer of a phi D torus, and is the normalizers, and you know that these characters extend. That was done in 2007. but now you have the question how these automorphisms act on that, and that's not done in type D. So that, yeah, it's type D. So with all its odds.